thanks everyone for inviting me. Happy to come and give a talk. So good morning, afternoon, evening, wherever you are. It's morning here in Seattle. So as she mentioned, I am going to be talking about quantum learning algorithms, implying some circuit lower bounds. This is joint work with Srinivasan Arunachalam, Alex Grillo, Tom Gore, and Igor Oliveira. And I think one aspect that I really like about this work is that it's one of those things where the design of quantum algorithms is somehow used to connect the upper bounds into lower bounds and circuit complexity classes. I may not be able to see the chat or something, so as Subhashi mentioned, please feel free to interrupt me if needed, and we'll take it as it goes from there. So let's get into it. So the first thing I guess let's discuss is what are circuit classes and why do we care about these lower bounds? We are all familiar with Boolean circuits. You have some inputs, you have some gates, and you have outputs. And there are multiple ways with which we would like to parameterize these circuits, the fan in and fan out of each gate, what kind of gates are allowed, how many numbers of gates that you want to put in there, polynomial number of gates, just constant, do you want only constant depth, and so on and so forth. And in this case, we won't go into too many details about what circuit class we're talking about, except that we'll talk about some generic circuit classes. And the size of the circuit class being S of n, we'll say that it's C of S of n. Unless specified, it's mostly polynomial size circuits that we care about. So now that we have Boolean circuits, what does that even mean? We say that a language L has circuits of a circuit family C if there is some family Cn here, such that Cn of x is 1 if and only if x is in the language. So somehow the circuit completely characterizes what this language is. And there are two kinds of circuit families that you can think of here. The first is uniform circuits. This is what you would come across when you design algorithms and when you write your programs, where you just take some input length n and you can output a circuit for that input length. So there is a prescribed way to construct these circuits in a very standard fashion. But there need not be connection between the way you construct the circuit for input length n versus something you construct for, let's say, input length n plus 1. So it could be an arbitrary collection of circuits for any input length. And when there is no connection like this, you say it's a non-uniform circuit family. Why should you care? Because most of the time when we think of it, when you think of algorithms, you run into things that are uniform. Well, non-uniform circuit families tend to do some very crazy things. For instance, they can, for a fixed input length, you can think of them as actually solving the halting problem. What does that mean? Well, let's say that for an input length n, I take an input 0 to the n, and that it's in the language if the nth Turing machine halts. So, the string n constructs some kind of a Turing machine, and if that Turing machine halts, then it's in the input. So for some fixed input length, maybe you have a structure there, but for length n plus 1, maybe there is no structure in there. And somehow a non-uniform circuit family, by collecting just arbitrary circuits without any structure in them, can somehow solve the halting problem. So you have some weird things happening here. Then the question becomes, how do we sort of understand or relate the power of uniform and non-uniform circuits? And that's where circuit lower bounds comes into the picture. Hopefully you want to be able to separate these things or show that they are different or they do some very different things. And there's an explicit way of proving that. As with almost every question that complexity theorists care about, it comes back down to the P versus NP question, right? And circuit lower bounds can be thought of as some kind of a combinatorial way to resolve this problem. What does that mean? I can always rephrase the question to say that, maybe I want to show that now NP cannot be solved by polynomial size circuit families, right? Maybe it's a controversial opinion, but it is sort of believed, but we don't have an explicit proof to kind of say that. But then, and this is both for either uniform or non-uniform circuit families, right? In the case of non-uniform circuit families, you kind of have these conjectures that if it held, then the polynomial hierarchy collapses and so on, but there isn't an explicit proof. So let's make the problem a little easier, right? Now, maybe I can't say that NP can be solved by polynomial size circuit families, but can I at least say that it's not solved by constant depth circuits, right? This should be a much smaller class of circuits. Can I show this? And for now, at this point, we cannot show this. This is still a problem that we haven't succeeded in solving. There is some things we can show, for instance, that parity doesn't fall into this very small constant depth class AC0 and so on. But then beyond that, there isn't much more we can say. So let's try and make the problem easier. Let's say that can I take some very, very large complexity class and show that it cannot be solved by some very, very small circuit family. And here you start seeing some progress happening. Fortnow and Clivens in 2009 had a result which said that if you take any circuit class which has, let's say, a pack learning algorithm in polynomial time, then you can show that it does the class BPX, which is like an exponential time analog of randomized polynomial time, is not in the circuit class C. So that's one step forward. And there have been further developments in this area with certain different refinements. I won't go into the details of that, but let's say that one of the biggest results that we have in this area is to show that non-deterministic exponential time is not in this class ACC0, which was shown by Ryan Williams in 2014. And this is after many, many years of looking for circuit lower bound results. So what is next? Next is non-deterministic exponential time. And the class ACC0 is these constant depth circuits. They can have and, not, or gates, but they can also have these gates that do mod M. So this is still a pretty small class of circuits that you can think of. And it's taken many, many decades of work to even get this result. Right, so what is the quantum angle? Like, after all, that's why we're here. And we like to throw quantum in front of everything or into everything. So as quantum complexity theorists, I guess the question we care about is not just P versus NP, but throw in BQP there and try and figure out what happens in that case. Right, and one thing to note is that the classical techniques that exist may not necessarily help to separate quantum complexity classes. For instance, if NP and BQP are incomparable, the same techniques may not work. Secondly, if certain assumptions that work in the classical setting, like say hardness of factoring type or flavor of results, don't work in the quantum case, you need to move into new assumptions like hardness of LWE or so on and so forth. So you need to still think of what this means. So the problem then that you care about is, can you show that quantum computations cannot be simulated by any small classical circuits? And we don't solve the problem entirely, but we take one step probably in some direction, so that if circuit class C has non-trivial quantum learning algorithms, and I'll define what this means as we go forward, then you say that some very large complexity class, quantum complexity class, is kind of separated from C. So C is kind of strictly contained in that class. What is this very large complexity class? It's an exponential time analog of BQP. So that's the best that we can do. So this is like a very large class and a very small circuit class. So this is the first time we get these kind of generic results. And hopefully, as we go on, this keeps getting improved. Okay. So before maybe going into the details of what this means, let's first talk about what these non-trivial learners are and what the learning model that we care about is. So I say that a learning algorithm A for some circuit class C is trying to learn some unknown function f from this circuit class. It accesses it through some kind of a quantum oracle, and the following queries are allowed. So it can use random labeled examples. So let's say A asks for, give me some example, and you get X, f of X. It can continue to do that. It can also ask for what are called membership queries. So essentially it says, well, I have a question y1. You tell me whether f of y, what f of y1 is. It continues to play this game. And at the end of the day, it has to output a hypothesis. Now, I would stress that here, the hypothesis that we care about is a quantum hypothesis. By that, I mean that you're outputting the description of a unitary circuit. Why do we need this? Well, because in general, when you think about pack learning models, even quantum pack learning models, you output a classical hypothesis. But here we need it for two reasons. One is a quantum hypothesis is at least as powerful as a classical one. So you're looking at a stronger model. And hopefully by looking at a stronger model, the lower bounds that you get, it's a little easier to achieve them. But we also need it for a technical reason because we want to construct these hypotheses and build upon them in a black box manner. So if you have a quantum hypothesis, then you can kind of bootstrap the whole process and the rest of the proof easily. So that gives you the two aspects. What should this hypothesis satisfy? With high probability, it should be close to F. Oh, and I think I didn't fix this mistake. It should say the probability that you sample an X from a distribution, and this expression should be at least 1 minus epsilon, because this expression is computing what the error is, and you want the error to be, sorry, it's not computing what the error is, it's computing what, how well it agrees with f of x, because it's basically projecting and checking whether it's equal to f of x or not. So that should be at least 1 minus epsilon. And essentially you want to say that my hypothesis agrees with f of x very well, right? So you say that it's an epsilon learner for this distribution. If for every concept or every function in the circuit class, it outputs a unitary that has high agreement with the function with high probability. Now that we have defined what it means to be a learner, we can talk about when they are trivial or not trivial. So what is a trivial learner? One thing I can do is I could always query the complete truth table of F, right? Then you completely learn the function, you don't make any mistakes, but you take 2 to the n time to do this. But there's another thing I can do when I have a quantum hypothesis. I can do Fourier sampling. So because I'm accessing it through an oracle, I can basically do a quantum Fourier transform and then measure in the Fourier basis. What this gives me is one Fourier coefficient once I measure it. And I'm not saying that that's going to be a very good approximation to what f of x should be, but it's going to be something which does slightly better than random. And what I mean by slightly better than random is that the error is, let's say, bounded away by omega 2 to the minus n over 2. So you do something slightly better than a random guess, but not much better. However, you don't run into 2 to the n time. You can do this in polynomial time. So this is like the second kind of trivial learner that we have. So now that
Sorry, can I ask a quick question?
Yes.
Is this algorithm a quantum or classical?
The algorithm is a quantum because it's a quantum learning model. So it's a
then
quantum algorithm.
These membership queries can be done in superposition as well, right?
Yes, the queries can be done in superposition as well. Absolutely.
Okay.
Sorry, can I also ask a question, Aarthi?
Sure.
So in this second Fourier sampling algorithm,
yeah,
if you do Fourier sampling, you're going to get back some parity function, and you know that either that parity function or its negation has a small positive correlation with the function.
Yes.
How do you know whether you should take the parity function or its negation?
You just output either one with probability half. Flip a coin and put any one, and that's enough.
But now with probability 50%, you put something that's worse than random.
With 50%, I think if you flip a coin, I think that should take care of the fact that you are like 2 to the minus n over 2 away. If I'm not wrong. I mean, you're not saying that you're going to be worse than, you're going to be better than random every time, right? I mean, it is random. So you're going to have correlation either with the parity function or its negation,
right?
And you don't know which. And I'm saying that you can choose which one you want to output with 50% probability and maybe stick to that.
But now with 50% probability, you have something that's slightly better than random. And with 50% probability, you have something that's slightly worse than random.
Mm-hmm. But if each time you're sort of playing this game and you're choosing something, I mean, which is why I think you get to the minus n/2. I can get back to you on this point as to how exactly the calculation goes, but yeah, I will reach back to you that. But yeah.
I think there was also one question in the chat. Someone asks, does the output hypothesis not need to be in set C?
The output hypothesis, no, we don't put any restriction on what the output hypothesis has to be, because in this case, it's actually unitary, right? So it's not really going to fall into the circuit class that you care about. So yeah, you just wanted to have correlation.
Okay, thanks.
Anything else? Okay. So then I will move forward. Okay, let's maybe state the main result. So the theorem here states that if there is a class C of polynomial size circuits, and they can be learned under the uniform distribution with membership queries, and the error that they make is at most half minus gamma, then in quantum time, O of gamma squared times 2 to the n over n, I can show that this class is not this BQE, that is exponential time, exponential quantum time class is basically separated from this circuit class C. We want C to sort of be well behaved, and for that you say that it's closed under restrictions. All that means is that if I take any function that's in this class and fix some of the inputs, then I can still solve the same function with these restricted inputs in the same circuit class. So it's just saying that it's well structured and well behaved. Okay, so I'll go back to now talking about why this connects to these trivial learners. So let's take the first parameter of interest. It says that, let's say gamma is some constant, in this case 0.49, and let's say the time then in that case becomes it's order of 2 to the n over n. And the other parameter, let's say, that we care about is when gamma of n is something that's superlinear, n to the omega of 1 times 2 to the minus n over 2. And in this case, you get another superlinear time algorithm. Why are these two interesting sets of parameters? So this kind of matches to what you have with what we consider are these trivial learners. Why is that? Essentially, if you have something that runs in 2 to the n over n time, you make some mistake, but you're still faster than, let's say, brute force. And if you can do something that satisfies parameter 2, then you're being a little more accurate than Fourier sampling. So if these two are the cases you care about, then you're sort of doing anything that beats this is a non-trivial learner. So that's the idea. Okay, so let's talk about what is kind of the consequence of this theorem. What does that mean? Let's say one direct application. In previous work with Alex and Srinivasan, we had showed that if you have polynomial time quantum learners for the class AC0, which is like a constant depth circuit class with and not or gates, then polynomial time quantum learners don't exist for this class. However, what we know is that quasi-polynomial time learners exist for this class. And this is even a classical algorithm that was shown by Linear Mansoor and Nisan in 1993. So this is like n to the log a n. So in some sense, this is not telling us what happens with exponential time learners for this class. But what we care, but the consequence is that because you have non-trivial learners in this case, it essentially implies that BQE is separated from AC0. However, this is a direct consequence that even comes from classical algorithms, so it's not so interesting. What could be interesting is if we could show non-trivial quantum learners for, let's say, certain bigger classes like ACC0, or maybe depth to threshold circuits, which are some kind of a, they represent certain feed-forward neural networks and so on. So it's a pretty interesting class to think about. So if you can show non-trivial quantum learners, then you're going to make some breakthrough in the complexity theoretic bounds that we have. But in general, I would say that there is always two ways to interpret this, as with everything in life. If you're feeling very optimistic, then you're going to be happy that there are new paths to prove circuit lower bounds, and that you can maybe develop these techniques and show more results and help us understand quantum complexity classes better. But maybe you woke up on the wrong side of the bed, you're not feeling very optimistic, then essentially this is telling you that there is some evidence that even getting provable advantages for quantum learning algorithms is difficult. Because this is saying that even showing that you do something that is polynomially faster than brute force is actually going to show you some big complexity theoretic breakthrough. And very smart people have worked for very long times on these things, so we expect these problems to be hard. So you can take it whichever way you feel like. So that I would say is an overall consequence of how we view this result in the larger context of things. So before I go to the proof, are there any other questions? Nope. Okay. Let me give then a full overview of the roadmap that we take for this proof. There are three basic steps. The first step says that if you have a quantum learning algorithm, then it implies something called a quantum natural property. What are these quantum natural properties? Well, intuitively, what you take away from this step is that if there's a way for me to learn this circuit class C, then I can distinguish it from being a random function, because I can essentially learn it with high correlation. But think of a quantum natural property as being some combinatorial object that helps you identify that, here there is no structure, or there is absence of structure here, or it separates everything having a specific kind of structure from things that don't have it. The second step is assuming that if P space is hard for some complexity class, in this case, quantum sub-exponential time, then there exists a pseudorandom generator, that's what a PRG is, that is secure against some uniform quantum complexity class. And the construction here is a classical construction, but the proof that we show is that it has to be secure against quantum complexity classes. So the main contribution or the technical meat of our work sort of exists in showing the security in a quantum setting. So the first thing that we take is a P-space complete language, which was designed by Trevson and Wadden in 2007. And you take a language that is mildly hard, let's say. So and you want to amplify the hardness, because at the end of the day, if you want to get a very good random bit out of it, then you want to be able to get some hardcore bit conditions satisfied and so on. So how you do that is some kind of a hardness amplification. The references here are not talking about the construction, but kind of they're talking about, let's say, the security proofs for these constructions. So to amplify the hardness, you use the idea by Impagliazzo et al., and you use the Goldrack-Levin theorem to kind of get some hardcore bit conditions out of it. And the first of these comes from ideas from local list decoding and coding theory and things along those lines. Next, we have to convert this amplified hard function into something that extracts a random bit or a random string out of it. And for that, we use the NISAN-WIGDERSON designs that exist and that are well known. And then now that we have the PRG that is constructed, and once we prove its security, which is our main contribution, we can go on to the next step. The last step is how do you use this PRG and these natural properties to put it together? And you use it using the best kind of an argument, which is a win-win argument. You say that if your P space is, suppose it was easy for this complexity class that you care about, then there is a very straightforward way to prove that it's contained in an exponential time complexity class. This actually comes from previous classical results that exist. So, using some diagonalization arguments, it becomes pretty straightforward. But what is more interesting is to show the second part. It says that if this language is hard, which is our assumption, right, that it's not contained in some sub-exponential time class, then our PRG by step 2 is actually considered to be secure. And if it is secure, then somehow my natural property has to think that it is a hard function. And if my natural property thinks it is hard, it will accept it. And somehow that is how you make it work. So this is the main roadmap that we have. Any questions at this point? Okay. So let's get into this. So the first thing is, what are quantum natural properties? So the idea of natural properties comes from Rasparov and Rudich in '97, for which they eventually got a Gödel Prize, I think 10 years later. Essentially, it is some combinatorial property P that holds for a large fraction of all possible Boolean functions. So like I said, it identifies the absence of structure, which means it's a property that permeates many, many functions that you would care about. But you should be able to decide if some function satisfies this property P efficiently for it to be useful in any sense. And with high probability, let's say at least half, you want to say that random functions satisfy this property. So this kind of helps to satisfy the large fraction condition. And at the end of the day, you want it to be useful in some sense, because if you have to identify absence of structure, you have to say what the structure is. And in this case, you say that the structure is defined by some circuit class, and you say that the property is useful against a class, where if the function satisfies the property, then you can definitely conclude that it's not in the class. So that's how it works. So it kind of flips around what you would intuitively think of. For example, now if I say that there is a language L in P space that satisfies this combinatorial property P, then I can conclude, let's say that P space is separated from this circuit class. So what are quantum natural properties then? The easiest way to think of them is to think of them as a quantum algorithm D that satisfies certain properties. Here we have bounded quantum polynomial time. So the property that we get is also going to be a promise property in the following sense. So it has to be, again, run efficiently, but here efficiently means it runs in polynomial time in the size of the truth table of the function. So you get a big function as the input, and you run in polynomial time in the truth table size of that function, and you want to be able to decide whether f satisfies the property or not. There is a density question involved. So you want to say that if there are 2 to the n possible Boolean functions on, that take n bits as input, then at least half of them should satisfy this property. And here, satisfying the property essentially means is that with very high probability you accept if you satisfy the property. And if you don't, on the flip side, it is useful because anytime the function is in the circuit class, you reject with very high probability, or you accept with very, very small probability. And this separation gives you the promise behavior and satisfies the fact that it's a quantum natural property. So it's easiest to think of it as just a quantum algorithm that satisfies certain conditions. Okay, any questions at this time?
So what are these probabilities taken over?
The probabilities are, it's a quantum algorithm, right? So it's the probability with which so you run the algorithm, measure the output bit, the probability with which it outputs 1.
Oh, I see. The whole truth table is one big input.
Yes, the whole truth table is your big input stream.
Thanks.
Okay. So now that we have quantum natural properties, we can talk about what this, how to connect it to a learning algorithm. So the lemma says that for some gamma that is omega of 2 to the minus n over 2, if my learning algorithm can epsilon learn the class in this amount of time and makes this amount of error, then there exists a natural property that is useful against this circuit class. Okay, so how do you construct it? I'm given the truth table of the function because let's say I have that's my input, and I construct the algorithm D in the following way. I basically run the learning algorithm, and every time the algorithm queries my function, because I have the truth table, I can answer even superposition queries and so on accordingly. A will output some hypothesis, a unitary here. And now what the algorithm does is it picks t different random inputs x1 to xt. And t here is going to be gamma of n, 1 over gamma n cubed. I run the unitary on each of these inputs separately. So this is like one run at a time. And I get these classical bits on measuring the output B1 to BT. And they have to satisfy the following condition. I output 0 if and only if, you know, the correlation factor here, whether BI is equal to f of xi, it's f of xi then, not fi of x, is at least half plus gamma of n over 4. So why does this procedure suffice? Essentially, you have constructivity. You can run this whole thing in polynomial in the truth table time, which is what you care about. Why is this useful? Well, because A is a learning algorithm for the circuit class, then the output, the hypothesis that it outputs has a half plus gamma approximation for F. So by doing a Chernoff bound, if you just compute how much correlation that it has, in this case, then you will say that it has high correlation with the function. And if it has high correlation with the function, because my natural property does the opposite of what a learning algorithm should do, I will output 0. The next step is, how does this satisfy the density condition, right? Because you need to say that if it's a random function, I need to accept with high probability. And you can do this with some sort of a counting argument. So by counting all the different kinds of hypotheses that can be output, unitaries of this particular size that can be output, and the number of random functions of that take n-bit inputs that happen, you can find that this hypothesis will not approximate your random function very well. So it's not going to have high correlation with any random function. And because of that, by doing a Chernoff bound, you will find that it doesn't satisfy this condition. And so in that case, your natural property will accept a random function with high probability. So that is the main idea that is used. So you use a learning algorithm to construct the natural property in this case. So the second step, now that we have done that, is to construct this conditional pseudorandom generator. So let's see what the construction says. My assumption here again is that P space is hard, so it's not in sub-exponential quantum time. And there are certain parameters here that I can generate this family of generators. And this generator, we want it to be uniform, so that construction is easy in later parts of the proof. It says that this generator has a stretch that takes L of n bits of randomness and extends it to M of n. Here, think of L of n as being something that's superlinear in n, so it's n to the alpha, and it stretches it to something that is a sub-exponential in n. So you don't go from linear or polynomial to a fully exponential stretch, but you get something that's a little smaller than that. So the uniformity condition essentially says that it can be efficiently computed for any input length that you care about. And it has to satisfy a pseudorandomness condition. So it says that given in this case, this is your discriminator, let's say. So given any circuit family that is uniform, the probability that my distinguisher in this case can take a random string and output 1 versus the probability in which I can take the output of my generator and output 1, they're not very far from each other, right? So this is your basic pseudorandomness condition. So now this gives you your conditional PRG. I'm not sure how time will go, so I won't go into the details of the construction at this time, but I will come back to it if we have time as we go on. Any questions at this point? Okay. So the last part of the puzzle we need is to connect these natural properties now to lower bounds. So we say that for every circuit class C, one of two conditions holds. Either for every natural number k, there is some language Lk that exists in quantum exponential time, and that cannot be computed by general Boolean circuits of size n to the k, right? Which gives you your separation. Or there exists some constant nu greater than or equal to 1, such that if you have a natural property against this circuit class, then deterministic exponential time itself is separated from this circuit class. And because BQE contains E, you kind of get this for free. I think that should be flipped, right? Yeah. It's the wrong ordering. Okay, so how is the proof sketch? So the main idea was inspired by work done by Oliveira and Santhanam, where they get a similar result for randomized exponential time circuits. And the first step, like I mentioned, is inspired from what they have. And in this case, you assume that P space is actually easy. There is some sub-exponential quantum time algorithm for it. Then you can construct this language LK that is contained in P space, but with just some diagonalization arguments and and counting arguments, you can show that there exists some Boolean circuit that will not be able to compute this language L to the K, LK. And that kind of gives you your first step. So that is the easy part of it. We care more about the second step. And now, assuming that you have this hardness condition, the previous PRG that we constructed, we use that, and we use a quantum natural property B that's going to be useful against this circuit class, because that's my assumption, and do the following. I'm going to construct a function Hn here that takes t bits as input and 1 bit output, where t is some polynomial in n. I will show that this can be computed in deterministic exponential time. And finally, you'll show that if this PRG is actually secure, as per our assumption, it does not have circuits that fall in C, in the circuit class C and of size n to the A over nu. So that is the idea. So maybe we can dig in a little bit into how this argument goes. So, okay, now first thing we do is let's take this PRG, and I can always think of the output of this PRG as the truth table of some function. So now this is like an m of n bit string that you get for every seed w that you put in, you get an m of n bit string, and that is the truth table of some big function. Now because my PRG is secure, there has to exist some w here, such that my natural property cannot distinguish this gn of w from an absolutely random function, which means my natural property has to accept with high probability. So let's try and construct our language on the basis of this random function, right? Because I need a unique way of constructing the language, I can always say that my language is just the first such gn of w that is outside of my circuit class, or that is random, let's say, that is accepted by B. But you run into a problem here because we have a promised natural property, and computing exactly the probability with which my algorithm B is going to accept this gn of w is hard. And I can't do it in like exponential time. I need to do it with high precision, and I don't have enough time to do that. So you run into a problem here. So you need to overcome this. So what you can do instead is say, I'm not just going to take the first gn of w, but let me change my input slightly. It's going to be the seed plus an index. And I'm going to say that the exit bit of Gn of W is 1. That's going to be my language now. Because the main bottleneck that you have here is just the way the bottleneck of computing the generator itself, it runs in deterministic exponential time. So it's fine. Now I don't need to find out the specific W per se for which it's hard, because the language is simultaneously computing for every possible W and X that you give as an input. Now let's assume by contradiction that this language is actually in my circuit class. Essentially, that means that for every W, my generator string can be computed within the circuit class, but that violates the security of the PRG. And so that's how you get the contradiction. So somehow the security of the PRG and the natural property can be used to show this contradiction. And we kind of also show how you do this. Let's say, we have these conditions where the assumption is that you have a natural property against circuits of size n to the A, but there is some loss because the stretch is not, completely exponential. So you have some loss in showing that you only get something that's in n to the A over nu. But that just comes by all the assumptions that you use. If you replace the constants correctly, you will be able to prove that. There's no more intuition into this beyond that. So this basically is the last piece of the puzzle. Before I go into the construction of the PRG, are there any questions I can answer? Okay, if not, let's go ahead and try and construct this thing, or maybe deconstruct this thing, because you have to prove its security. So this is just a placeholder to help us recall what it was. You have some function family that has this kind of stretch for a seed of this length. It's uniform, so it has to be efficiently computed, and it's pseudorandom. So you need to show that a random string plus versus output of the generator, cannot be distinguished with high probability. Okay. So the first thing that you do is you choose a p-space complete function f, and you want it to be downward and random self-reducible. What this essentially means is that it's a way for us to get rid of this non-uniformity condition that is there. That'll keep showing up, because if you want it to be secure against a complexity class, you don't want it to be secure against circuits that run in certain time, which could be non-uniform. So you have to get rid of any non-uniformity that you find along the way. We amplify the hardness of this function. So you take the function and you take its k-fold version, where every coordinate you act upon it with the function. However, this gives you a non-Boolean output, and you want it to have a Boolean output, and you want a hardcore condition. So essentially you take some random string and of length k, and you basically take the inner product of fk of x with r to kind of get you your really good random bit. And finally, once you have this, you put it into the Nisan-WIGDERSON design, so it works and you can get a secure PRG out of it. That's the basic construction. But now if you want to show that it is secure against quantum computations, you essentially want to prove that if this PRG is not secure, then somehow you are going to violate your assumption. And our assumption, so basically you want to go in the reverse direction is what I'm saying. But what is our assumption? Our assumption was that p-space was hard for sub-exponential quantum time. So somehow what you precisely want to prove is that if this has a distinguisher that succeeds, then there exists some gamma such that p-space can be solved in sub-exponential quantum time. That is the main crux of the construction. And we can sort of go into the steps. So the language that you construct is from Trevisan and Waden's p-space complete language L star. It's also complete with respect to polynomial time reductions, which is what we need. And the idea of being downward self-reducible, essentially think of it as, if I have to have an algorithm to be solved for input length n, suppose I know how to solve it for smaller inputs, then there's a very nice recipe where I can use all of those to build my algorithm to solve it for input length n. Okay. And when I say random self-reducible, it just tells me that if I have a good algorithm that can solve it in the average case, then I can use it to construct a good algorithm that also solves it in the worst case. So there are some very nice behaviors that you want baked into this language so that you can use it for our purposes. So the next step is this uniform hardness amplification business. So remember, we're going in the reverse direction. So once you have the language, when I go in the reverse direction, I essentially want to say that if I can solve my k-fold repetition of the function with certain probability, then I can solve one application of that function with some good probability as well. So the main idea here, well, maybe let me state the theorem and then talk a little bit about that. So here you're taking some polynomial number of repetitions, and you're saying G is a quantum circuit that takes x1 to xk and acts on f to the k of x. So it's basically f of x1, f of x2, f of x3, and so on. And this circuit, let's say, can in expectation, it can compute this function with probability at least epsilon, right? So that's the kind of correlation. And this epsilon is very small. It's omega of 2 to the minus square root n. So, it's exponentially small. But if I can do a k-fold repetition with that probability, then I can construct a quantum circuit B. It's still polynomial in the size of G and N and so on. So there is not that much of a blow up or an overhead. But in expectation, I can solve the function, one application of the function f of x with only, 1 minus 1 over poly error. So I can solve it very high probability. So there is only 1 over poly error involved in that case. Just for technical reasons, because you want this recipe to be efficient, you have the idea that you can manipulate the code and construct the circuit. But the main idea is kind of here. And this is probably where the technical meat of the paper lies. This is like a quantization of a result by Impagliazzo et al., which uses ideas from local list decoding and so on, where you think of the k-fold repetition as some kind of a code, and kind of believe that if you have a list of errors on, let's say, different coordinates, then somehow you can use it to still distill the correct answer on one coordinate efficiently. And there are challenges that exist here, mostly that come about for a very, very straightforward reason. And that is basically that in the case of randomness, classical randomness, you could always restrict the randomness or fix the randomness, and then all you have to do is a deterministic analysis. And once you do the deterministic analysis, it kind of follows through very nicely for a convex combination of fixed randomness as well. But in the quantum case, there is no way to fix quantum randomness. And because you can't do that, there's a lot of subtle analysis that you need to do to make all of the arguments work in a similar fashion. But the main reason that happens is for this very simple thing that you very commonly run into, pretty much all of the time, I guess. I won't have time to go too much into the details of that, so maybe let me not do a hodgepodge version of it, and if there's time, I'll try and get back to it. But as far as the reconstruction goes, here we are going from this k-fold repetition here to solving just the function itself. The next thing is reconstructing the step of Goldreich-Levin, and this result basically comes from Addock and Cleve in 2002, which says that if there is a quantum circuit A with an m-bit workspace that can solve, that can take some random string r and this input x, and computes f of x times r with correlation half plus gamma, so we can do it with probability at least half plus gamma, then there is a quantum oracle circuit that can compute just f of x with probability at least gamma cube over 2. And there exists, let's say, a uniform algorithm that can be used to compute this efficiently. The way to prove this is using some kind of Fourier sampling to kind of extract what this R is, and then use that to reconstruct f of x. So it's a pretty standard result. So we use basically the result by addict and cleave, and only make sure that there is no extra overhead here and everything fits in nicely. So this is like the second step of that reconstruction, where you go from GL of f to the k to f to the k. And now we need to like figure out what happens in the last step. So the last step for that, you kind of sort of need to understand what the generator itself does. Intuitively, it does the following. Let's say there is a string of length m. I want to kind of construct subsets of indices of the string. Each subset is of size n, and there are t of these. And I say that each distinct subset does not have too much of an overlap. Right? The overlap here is limited by alpha. So that's how I'm going to break up my m-bit string. And they have some overlap, but not too much. And we know that there is actually an efficient way to construct these designs. So given some constants and given some parameters, then in polynomial time, I can easily construct what these subsets should be and which designs I need to, which indices I need to pick out for each set. And so now the generator essentially is going to say that I have some function f that takes n bits as input and gives 1 bit of output. So the way I construct it, given some design, is I compute it on the set S1 of indices, then compute it on S2 of indices, ST of indices, and just string them all together to get a t-bit string. And that's my generator in this case. And the algorithm essentially says that if I have a function g that goes from n bits to 1 bit, and I construct this design, and there is some quantum circuit D that can distinguish the output of this generator from a random string with probability at least gamma of n, then I can construct a quantum circuit that can also compute g of x with probability at least half plus gamma over 2t of n. So essentially it's saying that if I can compute the design, or if I can distinguish the design, then I can also compute g of x efficiently for some random input x. And the main idea here is kind of to say that what the design is doing is it's computing it on different sets of indices, and somehow if let's say it's the ith bit of it's the ith bit of the generator that you can distinguish with high probability, then you need to do some smart arguments to kind of sneak in this question x into that ith index, so that you can kind of distinguish that and compute that with high probability as well. So that's basically the idea. So this is kind of, let's say, the last step of your conversion, which basically gives you your reconstruction in a step-by-step process. Let's kind of, put it all together. So, when we constructed it, we had this hardness assumption, and you went along this route. So how do you kind of prove? Let's say I have a sub-exponential time distinguisher. So this gamma is basically 2 to the n, is at least 2 to the n to the lambda. And oops. And if you keep going back up, I know that I can compute the NISAN-WIGDERSON design with probability at least half plus gamma. Then I use the Goldreich-Levin theorem, or the quantum version of it, to be able to compute, this is some fk of x dot r, so I can compute fk of x with high probability. I take it up, using the hardness amplification to say that this means in expectation, I can compute the function itself with high probability. And now I can use all of that downward and random self-reducibility business to say that it's not just an expectation over X, but for every X, in fact, I can compute the function with high probability. And since all of this just had a polynomial sized overhead, the algorithm that I get is still, sub-exponential in size, which means you kind of get your violation happening here. And so you kind of now have constructed an efficient distinguisher for the PRG. So essentially this completes the last step. And so this is the last piece of our roadmap, where you started with the learning algorithm implying a natural property. We constructed this PRG, and then we showed how to put both of those things together to kind of prove our result. And I will stop at this time because I think there's just about 1 minute left with some open questions, and leave it for, yeah. So thanks, and I'm happy to answer any questions.